to add vectors that are moving in one direction, we are going to add the numbers if they're in the same direction, or take the difference of the vectors if they are in opposite directions, and then we're going to keep the direction of the longer vector. So here I have 10 meters per second east. I have 5 meters per second east. So in this, I'm going to include the magnitude and direction. So what I want to do is I'm going to draw the sum of the two. All right, so this is together. This is going to be 10 meters plus 5 meters. So that's going to be 15 meters to the east. Okay, now here I have 9 meters right and 3 meters left. So I'm going to say for this one we'll go 9 meters minus 3 meters. I'm finding the difference because for this case they're different directions. So I have 6 meters, but notice the 9 meters is the longer one. So I'm going 6 meters to the right. So then I would draw that one. It's going to look something like this. So 6 meters to the right. Okay. We have 2 meters left. Oops. And 7 meters. This should say left. So let's change this guy up a little bit here. You know. All right. So this is also left. So when we add these together, we're going to add them because they're in the same direction. So I have 2 meters plus 7 meters. So that's going to equal 9 meters to the left. So that'll look like this. And then I have 9 meters west and 2 meters east, which means we have to find the difference. So that's going to be 9 meters minus 2 meters. That's 7 meters. But here, west is the bigger vector, so I must be going 7 meters west. So that's the direction I need to draw. So 7 meters, 7 meters to the west. Okay. Now for part 2, we are going to also add the vectors, but now we have 2 different dimensions, all right? So 2 directions. We want to draw from tip to tail. We're going to draw the resultant. But for this one, we are only going to take a look at the magnitude of the resultant vector. We're not going to worry about the direction of the vector. So what we have, if I draw tip to tail, I can take the tip of the arrow here and attach it to the tail here. So I'm going to go ahead and redraw. So I have 12 meters and I have 5 meters. So the resultant vector is going to look like this. So this is what my resultant vector looks like. And now I need to find the size. Now, if you remember your Pythagorean triples, this is actually a 5, 12, 13 meter. So, so this would be my answer here. If you didn't remember that though, then you can just use Pythagorean theorem, and that's going to be 5 squared plus 12 squared is going to equal our resultant vector. I'll give that an r squared. And then you just take the square root of both sides, and then you get r equals 13. Okay, coming over here, we have, we need to draw again tail to tip. I guess for this one, what I'll do is I'm going to take this vector and I'm going to put it on the tail, or on the tip of this arrow. So this is 16 meters down. So the resultant vector, I start here and go to the tip of the arrow. So this is my resultant vector. So that's what the shape of it looks like. But now I have to figure out what the magnitude of the size is. So again, we can do 9 squared plus 16 squared equals my resultant vector squared. All right. If you recognize this is a Pythagorean triple, This is, oops, this is supposed to be 12. This is not a Pythagorean triple. So now I need to use my calculator. So I get 9 squared. I don't know if you can see that here. There we go. 9 squared plus 16 squared. And then we want to take the square root of that answer. And so then we get 18.4, we'll say 18.4 meters. So R equals 18.4. So we have to take the square root of both sides. Okay. So we have the direction is going down. Notice that's signified by the arrow here, and then 18.4. For part 3, we're going to label each item as S for scalar, and we're going to do a V for the vector. Let's go, I guess, let's do green. So V for vector. So I'm going to look around for the scalars first. Now a scalar is any number without direction. Okay, so 5 miles per hour, I don't know what way, that's got to be a scalar. 4 carats, definitely a scalar, it's just a count. Upward is a direction. Position has direction, that's left, right, up, down from the origin. Distance does not have direction, that's a scalar. Speed does not have direction, that's like 5 miles per hour. Velocity does. East has, this is a velocity, 6 meters per second east. It's speed with direction. 8 minutes is a scalar. Left is my position, 2 feet left, that's a position. Grams is a scalar. Meters, I have a distance, so that is a scalar because it has no direction, which means everything else must be a vector because it has direction. Okay, last one. In the Sphero lab, the Sphero started at the origin and was programmed to move as indicated. So it moved 6 meters to the right, 10 meters to the left, and then 2 meters to the right. So the question is, what was the Sphero's total distance? Well, the total distance is really simple to find because they tell us the meters that they're moving. So this is going to be 6 meters plus 10 meters plus 2 meters. So the total distance is going to be 18 meters. Then the next question asks for the total displacement. What's the Sphero's final position from where he started? So we can certainly draw vectors to do this. So I'm going to set this as the origin. And what's going to happen then is we're going to go 6 meters to the right. So 6 meters to the right. And then 10 meters from here. So if I draw tail to tip, my next vector is going to be here. I'm going to kind of put it a little further down so we have some space so I can see it since it's the same direction. So we have 10 meters to the left. And then we go 2 meters to the right. Okay, so what's happening then, if I put all of this on top of each other, what I'm looking for is the resultant vector, and the resultant vector is right here. This was the origin, and this is the end. This is my resultant vector. Okay, and this was 2 meters to the right. So if I go 6 here, and I go 10 this way, then this means that I have 4 left over here. And then I have 2 back to the right, so this must be 2 meters to the left when all is said and done. Now, for a lot of you, drawing those scalars is pretty tricky. Another way we could do this is we could add all the positions in order. So I went 6 meters to the right, so that's a positive 6 meters. 10 meters to the left would be negative 10 meters. And then 2 meters to the right is positive 2 meters. So when I add that all together, I'm going to have 6, that gives me negative 4, positive 2, that's negative 2 meters, which is 2 meters to the left. is a final position. So this is why it's important when you're finding displacement to make sure you add positive and negatives for direction, because what we're really doing is we're just adding the vectors together.